auto record on this computer. Right, good morning everyone and welcome to the Center for Theoretical and Computational Physics weekly seminar. Today we are very happy to welcome Alenka Mertelj from the Jozef Stefan Institute in Ljubljana, Slovenia. Alenka did her PhD at the Jozef Stefan Institute. She then spent some postdoctoral time in Germany and then went back to the Jozef Stefan, where she's more or less been ever since. And she's been very kind to accept to tell us about her very recent work on the ferroelectric Splay Nematic phase. So before I hand over to Alenka, can I please ask everybody to, as usual, mute their microphones and switch off their cameras during the seminar so we don't overload our internet connections. And that said, I hand it over to Alenka, please.
Thank you for the invitation. It would be much pleasurable if I could do that in person, but the situation is as it is. So I will be talking about recently discovered ferroelectric Splay nematic phase. What's not working? So first, I will say a few words about the nematic phases and how the polar nematic phase fits in. Then I will focus on the material and experimental results in which with which we show that this phase is ferroelectric. In particular, I will focus on phase transition between the nematic phases. And later on, I will show a comparison between a material which exhibits ferroelectric phase and a very similar material which does not. And at the end, I will discuss the problems and what is the outlook for this work. So first, why are we interested in polar order? Materials with polar order lack inversion symmetry, which gives them important properties such as piezoelectricity, flexoelectricity, and pyroelectricity. They are also optically nonlinear, which is good for second harmonic generation. And these properties makes them useful for conversion of electric energy to mechanical work or vice versa, as for example in electromotors, generators, or devices which use electroacoustic conversions, as for example ultrasound devices or speakers or microphones. They are also used in nonlinear frequency converters and in sensors, and they're also investigated for waste thermal and vibrational energy harvesting. And they're also interesting from the fundamental point of view, which is the main motivation for me. So nematic phases are the most liquid among the liquid crystalline phases. They differ from liquids only in that anisomeric molecules, either rod-like or disc-like, in the nematic phase on average orient in the same direction, which we usually denote by a unit vector called director. They have inversion symmetry, so the plus n and minus n direction are equal. That is why the order parameter of the nematic uniaxial nematic phase is a tensor, which can be in terms of director written as shown here. S here is the scalar order parameter, which tells how well are on average molecules oriented in the direction of the director. The ground state of the usual uniaxial nematic phase is a uniform alignment of the director, which makes it easy to prepare well-aligned layers of the nematic liquid crystals between two glass plates, as for example planar, which means that they are in the plane, the director lies in the plane of the layer, and the direction of the director is determined by the rubbing of the surface of the glasses. Or the other usual configuration is homeotropic, in which we treat the surface of the glass so that the molecules orient perpendicular to the layer. The nematic phases are biaxial. That is why we can study them by using polarized optical microscope. So any changes in the orientation can be seen by the optical microscope. because the ground state is uniform, any deviation from the uniform state will cost elastic free energy. And in the bulk, there are three fundamental deformations, schematically drawn here: the splay, the twist, and the bend. And K1, K2, and K3 are the elastic, orientational elastic constants, which corresponds to the splay, twist, and bend, respectively. The molecules, however, are not ellipsoid of revolution, but are more complex. They can be, for example, chiral. In this case, the nematic phase will also be chiral. In this, the director will exhibit uniform twist, as is shown here. Or in chiral materials, also phases made of chiral defects can appear, the so-called blue phases. The molecules can also be bent, like this one here. And you can think that if they're bent, then they will peg better when the bend is oriented in the same direction. And this is indeed what happens in some materials which exhibit two nematic phases. One is the usual uniaxial nematic phase, and the lower temperature phase is unstable towards bend deformation due to the shape of the molecules. But because you cannot fill the space with homogeneous bend, the bend deformation is combined with the twist in a periodic manner, as schematically shown here. And that is why this phase is called twist-bend phase. At the phase transition from the nematic to the twist-bend phase, the bend elastic constant exhibits slowing down, as shown here in this graph. There is a little turning up very close to the transition, but this is not yet fully understood. Before going to polar nematic phases, let's first forget about the shape, but just discuss the dipolar interaction and how the dipolar interaction can lead to polar order in liquids. Here, I'm talking about the liquids which are made of constituents, which can be either colloidal particles or molecules that have dipole moments and which in polar phase spontaneously orient on average in the same direction. If we look at a single constituent, in particular constituents, it means that the field at the position of these constituents, which changes with time because it's a liquid, must be large enough and must point in the same direction all the time so that we get the orientational order. This field is a sum of dipolar fields or of all other constituents, and the dipolar interaction has two main characteristics. One is that it very strongly decreases with the distance as 1 over the distance on the power of 3, which means that the particles, the nearest neighbor, will mainly contribute to the field at the position of the constituents we are looking at. And the second property is that it's highly anisotropic. Only constituents in one-third of the space, which is denoted here by these two cones, make the field at this position such that favors the polar orientation, while all the others in the two-thirds of the space will make the field which is in the opposite direction. And this shows that the correct positional correlations are crucial for the appearance of polar order in a liquid. And that is also the reason why polar order in liquid crystal is often associated with partial positional orders, for example, in symmetric phases. The positional correlations are strongly affected also by the shape. So if the constituents are disc-like shape, then the neighbors, which favors parallel orientation, will come closer, as you can see here, and it's more likely to have a polar phase in materials made of disc-like molecules, while in the rod, in the case of the rod-like shapes, The neighbors which favor antiparallel orientation will come closer, and this is also one of the reasons why the usual nematic phase, calamitic nematic phase, so made of rod-like shape constituencies, are polar. So if the constituents, in the case the constituents without head-tail symmetry, as for example, pear-shaped or wedge-shaped particles, which has what is called polar shape. Now, in this case, they can also form a polar phase, in principle, as schematically shown here. This phase, if the molecules do not carry a longitudinal dipole moment, this phase will be polar, but it won't be ferroelectric. But if they have if they carry dipole moments, then this phase will also be ferroelectric. The main difference between the apolar and polar nematic phase is that in the polar, the order parameter is a vector. And consequently, in the elastic free energy, we have an additional term, linear in Splay deformation. If the molecules carries the dipole moment, then this term includes so-called flexoelectric term, written here, which was proposed long ago, discussed by Robert Meyer. And with this description, the polar nematic phase is not uniform, but is unstable towards Splay deformation. This is the fact that was, again, long ago observed by Frank, and then more thoroughly theoretically discussed by Pleiner and Brandt, and recently it was also shown by density functional theory by Gregorio from the Ferrerini group. So now let's go to the experimental system. A few years back, Richard Mandel and co-workers designed a family of materials which exhibit two nematic phases separated by a weakly first-order phase transition. The molecules of the materials which exhibit this property have a few common characteristics. One is that they have a large dipole moment. Then they have a terminal nitro group, and they have a lateral group which gives this molecule a slightly wedge shape. Now I will show you a movie of the transition as seen by polarizing optical microscope. The material is placed in a planar cell, and the director is, the sample is rotated so that the angle between the analyzer and is around 20 degrees. That's only for to better see the feature of the transition. The number here tells for how much the movie is sped up. So this is the usual uniform nematic phase, but when we go close to the phase transition, you can see that strong pre-transitional fluctuations, which then destabilize this homogeneous alignment of the director in a stripe-like structure. Stripes are along the director. Then with lowering the temperature, the phase becomes more and more homogeneous, and after a relaxation, which happens with this wide defect line, the phase becomes homogeneous and look deceivingly like the uniform nematic phase shown observed at higher temperatures. So you could see in the movie that the fluctuations play major role in this transition. But before going to the details, I will say a few words about what kind of the fluctuations we have in liquid crystals for those who are less familiar with these materials. So there we see director orientational fluctuations, which are thermal fluctuations, and in bulk, their eigenmodes are plane waves with two branches, splay band and twist band. In a special case, when the wave vector of the eigenmode is perpendicular to the director, we have pure splay and pure twist mode, in which splay deformation periodically changes or the twist. If the wave vector is parallel to the director, both branches are degenerate, and we only see the pure band mode. These Eiger modes are overdamped, which means when they're thermally excited, they relax exponentially to uniform orientation with the relaxation times rates which are proportional to the ratio of the elastic constant and orientational viscosity. I already said that the nematic liquid crystals are birefringent. They're optically uniaxial with optical axis parallel to the director, which means that the director orientational fluctuations will be fluctuation of the optical axis, which causes strong scattering of light. And this enables to measure the properties of the orientational fluctuations by light scattering techniques, as for example, dynamic light scattering, or recently, when because imaging techniques becomes faster, we can use also microscopy methods, as for example, cross-differential dynamic microscopy, which was developed in our group. The advantage of these methods is that we can simultaneously measure the relaxation rates of the fluctuations in a wider range at small wave vectors, but more wave vectors in more directions simultaneously, as is shown in this graph here, where the relaxation rate versus the wave vector and its direction is shown. In a typical liquid crystal, nematic liquid crystal is 7, and you can see that in the direction parallel to the director, the relaxation rate increases much faster with the magnitude of the wave vector, and this is because the band elastic constant is much larger usually, and the viscosity much smaller for the band fluctuations. So now going back to our system, we have studied all three pure fluctuations in with the dynamic light scattering. And here are the results. We measured the relaxation rates, which gives us the ratio between Ks and viscosities. And you can see that band fluctuations are not affected by the transition at all, while both splay and twist fluctuations get slower. When approaching the phase transition to the second nematic phase, the splay gets much slower than the twist. To distinguish whether it is the elastic constant or the viscosity which causes this behavior, we also measure the amplitudes of the fluctuations, and this is what we get. The elastic constants are in this graph, and you see that the band and the twist are not affected by the phase transition, while the splay elastic constant strongly decreases when we approach the phase transition. I'm talking about orders of magnitude. Note that this scale here is logarithmic. This clearly shows that the splay fluctuations are those who destabilize uniform nematic phase at the phase transition. We also have observed that the orientational viscosity gamma 1 exhibit divergent behaviors close to the phase transition. So this is the first remarkable thing observed at this transition, this instability toward splay deformation. The second one is observed in the dielectric spectroscopy studies. Here in this 3D graph is shown frequency and temperature dependence of the electric loss, and you can see in the upper nematic phase, and you can see that there is a mode which becomes slower and which amplitude increases when approaching the phase transition, which is at 133 degrees. By doing the analysis of the modes observed in the electric spectra, we see the following. In the isotropic phase, we have the usual one broad mode, which gets slower when we go to the nematic phase, and by lowering the temperature, it becomes soon obvious that this mode consists of two modes. the usual molecular mode, noted with the red here, which corresponds to the rotation of the molecules around their short axis, and the collective mode, the blue one here, which gets slower and which amplitudes increases divergently when approaching the phase transition. So the amplitude of this is the collective mode, which shows the building up of the polarization. The amplitude of this mode is then also the main, is the one that contributes mostly to the static electric susceptibility. And the diverging behavior of the electric susceptibility is a characteristic of a phase transition to a ferroelectric phase, and together with the Splay elastic instability, this shows that this transition is a ferroelastic phase transition, and can be very nicely described by a Landau type theory. The theory which was in similar theory that was used by Schmidt and Selinger to describe the transition from the nematic, the usual nematic, to the twist band nematic. Here, the terms relevant for this transition are written. The first two are the elastic terms, the usual elastic terms for a nematic liquid crystal. The last two terms are by the lowest by symmetry allowed terms in polarization and the gradient of the polarization. Here the coefficient T is positive because the polar order in the upper nematic phase is not favorable. From the Landau theory, we also know that the Landau parameter in front the quadratic term is proportional to 1 over the electric susceptibility. So in our case, to the amplitude of the polarization mode. The middle term is a flexoelectric term, and it describes the coupling between the Splay deformation and the polarization. The gamma is Baer flexoelectric coefficient. So we have seen that the Splay fluctuations are those who destabilize the phase transition. So the most reasonable approach is to calculate the Splay deformation in the framework of this theory. This is technically very similar to to do the stability analysis of this energy towards small periodic fluctuations. Because of the coupling term, now instead of having separate director mode and polarization mode, the two modes are coupled. So we have two coupled modes. One is a hydrodynamic director mode, and the other is optic-like polarization mode. And this one is measured when the Q is 0 in the dielectric spectroscopy. This is the collective polarization mode. The director mode is, so the hydrodynamic mode is very similar to the usual Splay mode. The only difference is that we measure what I call here, where's the mouse? Here, the effective elastic constant, which is reduced in comparison to the true elastic constant by this ratio here, which is the Baer flexoelectric coefficient squared divided by the parameter T, which we set already that is proportional to 1 over the electric susceptibility. So the measured in this theory, the measured elastic constant is linearly depends on the electric susceptibility. And here a plot of the measured elastic constant versus the electric susceptibility or the amplitude of the mode. Polarization mode is shown, and it clearly is linear. We can fit it and get the Baer flexoelectric coefficient of this value, which is actually small in comparison to the values usually measured in the nematic liquid crystals, and we also get the true Splay elastic constant of 3 piconewtons. And what you can see here that at some value of the amplitude of the the polarization mode, this effective elastic constant will be 0, which means that this phase will become unstable for splay deformation. So what will happen then? First, let's have a look what the theory can predict. So obviously one solution would be a splay-like structure. And indeed, we can calculate, it can be done analytically, but also numerically. We get the structure as is schematically shown here, 1D periodic structure in which splay deformation is periodic and is accompanied by a periodic modulation of the amplitude of the polarization. Here, different colors denote the orientation of the molecules either in up or in down position, and with it also the direction of the polarization changes. Rossetto and Selinger showed that depending on the parameters of the model, 2D structure may be more stable than 1D. It depends also on the temperature where we are looking at. So what do experiments show? We used second harmonic generation imaging, which gives a signal in the bulk only when ferroelectric order is present, to study the evolution of the ferroelectric order during the phase transition. And in the region where optically we see the stripes, we also see stripes in the second harmonic generation imaging. These are dark stripes, exchangingly darks and bright stripes. And this can be explained by a periodic structure discussed before. The dark stripes correspond to the area where the polarization is 0, so it's the area where the polarization changes sign. The modulation period of this structure is between 5 and 10 microns, which shows that this phase is ferroelectric on the microscopic scale. So orders of magnitude larger scale than the molecular size. The evolution of the modulated structure can be also followed by looking at the splay band fluctuations by, for example, cross-dynamic differential microscopy. And you can see here in this image, the mouse is disappearing all the time, that just at the phase transition, just before the structure destabilizes, we have a slowing down of the splay fluctuations at some finite Q vector. In the movie, you have seen that in the region of deeper in the nematic, in the lower nematic phase, the phase looks very homogeneous, very similar to the uniaxial nematic phase. But response to the field, or just a little bit more careful optical observation, shows that this phase is not uniform, but that the director exhibits rotation in the plane of the sample, which the exact structure we are still investigating. We don't know what it is, but this rotation can be nicely seen in the dispersion of the orientational fluctuation, so the dependence of the relaxation rates versus the wave vector, which in the upper phase is, as expected, symmetric with respect to the rubbing, which, so the direction of the director in the upper nematic phase, which is denoted here with these white arrows. While in the lower nematic phase, it's rotated for a non-negligible angle. And then this is a question what this structure is. So there is obviously a twist. So is this structure a combination of splay and twist? And then there is a question whether the twist is a consequence of that the structure is confined and so frustrated, and then it just escaped in a twist deformation, or the twist is an intrinsic properties of this phase. The model, which is very good for the description of the phase transition, is obviously not sufficient there. So in order to understand better, or to know which terms we need to add to the model, we decided to look at the molecular origin of the phase. As I already told at the beginning, the family of the materials which exhibit this phase are very particular. So they must have this side group which gives the molecules a wedge shape. But what is a bit strange or surprising is that if we replace this terminal dipole, which is a nitro group, with some other dipole, the phase completely disappears. And that's why we say, okay, let's take two materials. So the one I was showing you the results before, and the one which is practically the same. The only difference is this dipole at the end of the molecules. And I must say, this study was much affected by the pandemic. The Rhea went to Bilbao, Spain, to perform the electric study of these cyano materials. She went there in March for a couple of weeks, but was stuck there for 3 months. On the other hand, Richard Mandel was not allowed to go to the lab, so he focused on virtual chemistry, so computer chemistry and molecular dynamic simulations. So what we observed, the orientational Splay elastic constant in the cyano material is also low for a nematic, but it does not have any strange temperature dependence. On the other hand, the electric spectra at high temperatures of both material is very similar, which is expected because both molecules have more or less the same dipole moment of 11.4 and 11.2 for RM734 and cyano counterpart respectively, and in both the angle between the dipole and the molecular long axis is around 20 degrees. And also in the cyano material, we observe, when we go deeper in the nematic phase, we observe in the megahertz region 2 modes, the usual molecular mode, the red one, and a collective mode. But while the collective mode in the RM734 gets slower and it grows, the one in the RM7 in the cyano material remain of limited amplitude. So to understand that better, as I said, Richard did some calculation. First, he calculated the energetically most stable conformation of both molecules, and as expected, they're practically the same. The only difference is in this end group here. He also calculated the energies associated with other conformers. So for the rotations around the AB, C and D axis, these energies are shown here, and you can see that the blue and the red curves corresponding to different materials are practically the same. Next thing he did, he calculated the most stable conformation of parallel and anti-parallel pairs in these materials. And here we observed that the angle between the molecular axis of the parallel pair of RM734 is much smaller than the one in the cyano material. In the first it is 8 degrees, while in the other is 27. This, of course, gives some clue, but it does not tell how the material will behave in the bulk, because in the bulk, a given molecule interacts with all its neighbor. And that is why Richard did the molecular dynamic simulation of both material in polar and in apolar situations. I don't have time to go into details here. I will just point out two observations. One is that the polar phase of the RM734 material has larger density for about 0.5%, which shows that these molecules can pack better when they're parallel. And the other observation was that in the cyano material, the polar phase exhibits smaller orientational order. If you look at the scalar order parameter for the cyano material, you see that in the polar simulation, the scalar order parameter is much smaller than in apolar one. This is in accordance with the larger angle which we observe when we look at the pairs. So how realistic are those simulations? We compared, in order to see that, we compared them to the small angle X-ray scattering, which is the right thing to compare with, because the small angle X-ray scattering gives information on the molecular positional correlations. While the cyano material, the scattering in the cyano material is what is expected for a typical nematic liquid crystal, in the direction of the director, which is here vertical, there is one peak at small wave vectors, while in the RM734, in both the uniaxial nematic phase and in the polar nematic phase, the scattering along the director is much weaker. And in addition, we observed two more peaks, which are denoted here. I don't see the mouse again. Here it is, 002 and 003. And when calculating the scattering pattern from the synthetic data, we observe in RM734 also three peaks, two additional ones, which are at the exact same position and as the ones observed in the experiment, and which this support the validity of the molecular dynamic simulations quite significantly. We also measured the relative density changes of the RM734 by placing it in a long rectangular capillary and measuring the length of the material when the temperature is changing. And indeed, we observed a jump at the phase transition from the usual nematic phase and the ferroelectric phase of, which is very small, of 0.1%, which is smaller than what is the difference between the polar and apolar molecular dynamic simulation. But this is what is expected, because we have seen, for example, from the electric spectroscopy, that the polar order already gradually grows in the nematic phase. So at the phase transition, at this weekly first order phase transition, only the density will only partly change. So only part of the density change will be happening there. So this brings me to conclusions and outlook. I have shown you that the phase transition between the usual nematic phase and the ferroelectric phase is a beautiful example, at least to me, of ferroelectric, ferroelastic transition. The lower temperature nematic phase is ferroelectric on the microscopic scale of several microns. And the experiment shows that the phase is not uniform. In a few degrees just below the phase transition, we see that it looks modulated, but later on we also see that the twist is involved. The reason for the non-uniformity is certainly the lack of the head-tail symmetry, which causes that the uniform nematic alignment is unstable toward the splay deformation, which of course the possible solutions of the structure with the splay are modulated structure or a regular or irregular lattice of the defects. The structure of the phase will be strongly affected by confinement, in particular if the size of the confinement is of the same size as modulation period or to the Splay curvature. It will also depend on the boundary condition, because now we have also electric boundary conditions, and to the history of exposure to external fields. And more metastable configurations are in confinement expected. Well, not only expected, we also observe them, but I don't have time to tell you all. We have seen that the density of the polar phase is smaller, which indicates that the molecules can pack better in polar phase, and also points out to the origin of the polar phase that it may be in the reduction of the excluded volume. Molecular dynamics simulations turned out to be quite realistic, and we think that they can be used to assist in design of future materials, in particular now with the limited access to the lab. One can play with ideas and see, and then only synthesize the materials that are promising, that show promise in the molecular dynamics simulations. We still need a microscopic model for the ferroelectric phase. While the simple model describes very well the phase transition, it's not sufficient for lower temperature, partially also because it lacks depolarization field, which is due to, in the bulk, due to the divergence of polarization and free ions which screen the field. If the director and the polarizations are parallel, then the Splay deformation is the divergence of the polarization, and in this case, the depolarization field will suppress Splay. However, you have seen that molecular axis, the long axis, and the dipoles are not parallel, so there is no need that the polarization and the director is parallel, and the phase can be biaxial. Then there is a question of, I have shown you that there is a twist. Is the twist a consequence of frustration, or it's an intrinsic property of the phase? And related to this is the question of the existence of Splay twist phase, which was discussed by Chaturvedi and Kamian this year, some time ago, yeah. And at the end, I have to comment the paper published by Boulder Group, in which they claim that the ferroelectric phase in this material is uniform. But this just is not what our experiment shows, and their claims are not based on some quantitative experiments, but they just say, well, you see that the phase looks homogeneous in also in the lower temperature, at lower temperatures. The same images I have shown you. But what good they did, they measured the saturated polarization values of 0.06 coulombs per meter. This is the value we also get, so we think it's a good value. And this value is also very large for a liquid crystal. It's less than an order magnitude smaller than of barium titanate, which is a classical solid ferroelectric material. I would like to thank and acknowledge my co-workers and funding. From Jozef Stefan Institute, these are Nerea Sebastian, Luka Cmok, Andrej Petelin, Irena Drevenšek-Olenik, and Martin Čopič. From University of York and University of Leeds, Richard is now in Leeds. These are Richard Mandel and John Goodby. The dielectric spectroscopy studies we performed in collaboration with Maria Rosario de la Fuente and Josu Martinez Pertiguero at University of Basque Country in Bilbao, Spain. For funding, I would like to thank Slovenian Research Agency and European Union. And I'd like to thank you for your attention. And I also invite you, those who are interested in this subject, to 18th International Conference on Ferroelectric Liquid Crystals, which we are organizing next autumn in Ljubljana. And we hope that it will be in person. So thank you.
Okay, thanks very much, Alenka, for a fascinating talk. This is now open for discussion. If you want to ask a question, please raise the little blue hand. If you don't know how to raise the little blue hand, just shout. So, who wants to be first? Who wants to be first? Praise, comments, questions, criticisms?
Ideas for a theory?
Yeah. Who wants to be first? Well, maybe I'll start. Alenka, you showed those two different molecules that you've compared the properties of. Can you just remind me what the differences were between those two?
Yeah, it's just, as you see, there is the different dipolar groups at the end of the molecule. One is a nitro group, which is not linear. That is quite a difference, while this one is linear. And I didn't went into detail, but if you look at these pairs, you can see that here the negative oxygen ion is actually attracted to the carbon ion here in this COO group.
Okay.
So they form such staggered pair.
All right.
So this is probably what helps formation of this phase and helps the packing. And because there is another COO group here, it's also possible that a pair, a slide which is even more shifted along the line, along the molecular direction, is possible to form. This is what we think is the origin also of these new peaks, which are observed in the small angle X-ray scattering.
Okay, but in both cases, the dipole is at one end of the molecule, right?
Yes. If you cut away this part, these molecules are practically the same.
Right. And what about its orientation? I think you said the dipole is not parallel to the long axis of the molecule. Is that right?
Yeah, it's correct, because to overall dipole of the molecule, there are more contribution. These two, the end dipole is along the axis, but then you have the dipole which comes from these COO groups, yeah, and then also from this methyloxy group here.
Right, so. Right, okay. So you have this roughly pear-shaped molecule with a dipole at one end, at the fat end. Is that right? Which is not aligned with the long axis of the molecule.
Yeah.
Right. Okay, very good. Thank you. Right. Any more questions or comments? Come on, don't be shy. So can I ask perhaps one more? So this theory by the Colorado people, does it just assume that your phase is uniform?
Yes. They don't prove it, if that's the question. They just say it's ferroelectric, and then they look at the switching of the field and say, well, it switches. It's polar. We know that it's polar. We know that it has the polar response. And if you have a polar phase, and if you put a field on it, of course you will orient it.
Okay.
Because the energy associated, because the polarization is so large, the energy due to the P times the field is much larger than the elastic energy, so you will be able to orient it with the field.
Okay. Just one more thing that you probably said, but I missed. Is this phase biaxial?
That's we don't know.
Because it looks a bit looking at the pictures you showed, some of the pictures you showed, it looked a bit, well, it's sort of like looking at some in plane order, which suggests it might be biaxial, but you say you're not sure.
No, I suspect it's biaxial. I suspect that that when the polarization and the director are not parallel.
Right. Okay.
Because if they're parallel, then the polarization field will expel Splay completely. But when Splay is expelled, then the density of the phase should decrease.
Right. Okay.
And what is suggested by the molecular dynamics operation, also the measurements, the density of the polar phase is higher, and that this is a part of the driving force, because it's difficult to imagine that the initial forming of the polar order, local polar order, is electric interaction.
Okay.
I would think it's more the way the molecules fit together. I mean,
so you mean it's probably excluded volume driven?
Yeah, excluded volume, but it's also, as you see, there are also attractive interaction between the molecules. So it's the excluded volume plus the attractive interaction between the pairs, which strongly depends on the shape, on the details of the molecular structure.
Sorry, by attractive interaction, you mean van der Waals forces and things like that?
It's also the electrostatic. Because,
also, yeah, okay.
Yeah, because as I said, that I think that the difference between these two materials, the final difference is electrostatics. As I said, that this oxygen is attracted to this carbon here, which is slightly more positive because of the oxygens here.
All right, thank you. Okay, any more questions, any more comments, suggestions? Feel free to speak your mind.
I also take criticism.
Criticism too. So this is your chance, come on. Well, looks like people don't want to take it up. So let's thank Alenka again, and
Thank you for listening.
and we'll be back next week with another seminar. Okay, so thank you all, and see you next week.
Bye-bye.
Thanks, Alenka. Bye-bye.